Welcome to our discussion on truth tables and equivalent statements. Here are the basic topics that we're going to cover in this video. Feel free to fast forward if you, stuff you already know. All right, let's start with conjunctions. A truth table, or the truth values of component statements, right, are used to figure out whether or not compound statements are true. So we do these when we deal with conjunctions. We're dealing with compound statements, P and Q or P or Q, those types of things. And then the truth values of those conjunctions are put into a truth table, and that just kind of helps us figure out when they're true, when they're false, if we have what's called a tautology or a contradiction, things like that. A tautology just means they're all the same. If you think of it as like total, tautology is totally the same kind of thing. Okay, so here's a typical truth table. We have these two statements, P and Q, and then we have the compound statement, P and Q. And basically, because it's an and, right, you have to satisfy both things. So when P and Q are both true, then the statement is true. So think of it simply as, a student will pass the test if they pass part P and part Q. So if they pass P and they pass Q, they pass the test. But if they pass the first part and fail the second part, they fail the test, right? If they fail the first part but pass the second part, they still fail the test. And if they fail both parts, then they obviously doubly failed the test, right? So that's the idea of a truth table. All right, here's a simple example. P is a statement 4 is bigger than 1. Q is a statement 12 is less than 9. Find the truth table for P and Q. Well, since 4 is bigger than 1, but 12 is not less than 9, then we know P and Q is going to be false, because if we go back to here, we have the first one was true, but the second one was false. So we're here in the second row, and we get that the conjunction, right, the putting them two together, the P and Q question is false. All right, disjunctions are ors, right? So when we have an and, we call it a conjunction. When two things are conjoined twins, right, are put together. Disjunction, disjoint, kind of apart from each other. That's your or questions. And the truth table for disjunctions are quite different. You'll notice that or is more relaxed, right? You can pass this test if you pass P or if you pass Q. So if you pass both pieces, you pass, right? If you pass the first one and fail the second one, you still pass. Fail the first one, pass the second one, you still pass. But if you fail both, you fail. So you see how it's almost the opposite of this one. This one had 1 true and 3 falses. This one has 3 truths and 1 false. So it's opposite in the number of things. It's just not opposite in the values, right? This one, the first one is true and the rest were all false. This one, the first 3 are true and the last one is false. So you can see that the top and the bottom are the same for both. When they're both true, it's true. When they're both false, it's false, regardless if it's an and or an or. See that? True to true, false to false, doesn't matter which one it is. But the middle ones are the ones that changes. When it's a disjunction and we're more lenient, all you have to do is have one piece is good and then it's true. A conjunction is more restrictive. You have to pass both, right? They both have to be true. So that's why those middle ones become false. So we can use that. And now, going back to the same thing, 4 bigger than 1, true. 12 smaller than 9, false. So what about P or Q? Well, because P was true, the whole thing is true because it's an or. It's basically saying, is P or Q true? And you go, yeah, P's true, so the answer is yes. All right, negations. Obviously, if we take the negation of P, everything just switches, right? True goes to false, false goes to true. Pretty simple and easy. How about if we want to kind of take disjunctions and conjunctions of, negations of pieces? It gets more complicated. If we're just doing just P, that's easy. But now we're looking at the negative of P and the negative of Q. This is where your truth tables are really going to help, only for keeping everything straight. All right, so here's P and Q. P is 4 greater than 1. That's true. Q is 12 less than 9. That's false. So obviously, the negation of P is false. The negation of Q is true. So here, right, the negation of P, that's false, and the negation of Q, that's true. So we're really asking what happens when you have false and true, and you can see it's false. All right, now let's look at this one. We've got the negation of P, which is false. Oh, and then we've got this new one, R. R represents 0 less than 1, which is true. Okay, so false and true. It's an and, so isn't that whole thing false? Okay, over here, negative Q, negative, I'm sorry, it's negation, but I always think of it as negative. That's true. P was true, so true and true gives us true. And then now if we look at this, it's asking for false or true, and you go true. That's how you want to tackle these things is, just like order of operations, you kind of have to work from the inside out. So the first thing we did was we worked on the negations. And then we figured out what's happening inside these parentheses. I got a false, I got a true, I'm doing an and statement, so that makes the whole thing false. Then I go inside these parentheses, right? And I go, all right, figure out what the negation is, that's a true. Nothing here, so that's just a true. Again, it's an and, so true. And then now that I've figured out what each of these parentheses are, I move outwards and go, okay, now I'm doing the union of those two, false or true. Yay, it's true, okay? So that's how you want to tackle those things. And the truth tables is just a way to help keep everything straight. So just make a table, start putting things into them, and then figure out, what's going on. So here's an example. We look at all this stuff. We've got P, we've got the negation of P, the negation of Q. So we start with P and Q. We figure out what not P and not Q are. And then we start doing pieces. Again, working from the inside out. So we look at the inside piece, and then once we know what that is, we can take it and do a conjunction with P. Now, when we're constructing a truth table, with no guidance, the previous example we had guidance. We knew what P, Q, and R were. They actually had statements associated with them. When we aren't given that, we just look at all possible combinations of P's and Q's. So we start with true, true, then true, false, then false, true, and false, false. You can see how these are just all the different 4 combinations we can have of P's and Q's. And then based on that, we do the negations, right? True, true, false, false becomes false, false, true, true, and so on and so forth. And then when you move to this, we're going, all right, we're doing a union of these two things. So false and false gives me false. But all of these are true, remember, because we're doing the or. So as long as one piece or more is true, these are all true. Okay, so now we've got the inner piece is all figured out. And now we're going to take that and do a conjunction, right? An and with P. So these are only going to be true, right? This thing is only going to be true when both pieces are true. So as soon as we have a false, we know it's false. We don't even have to remember what P is, but over here, P is true in this case, but it didn't matter. Okay, this one's true. P is also true, so they're both true, so we're good to go. This one's true, but P's false, right? So it's false, and same thing here. So that one's false. So we get in the end that this statement is, right, sometimes false, sometimes true. Now, the number of rows in a truth table, sure, it's always going to be 2 to the end, because however many letters you have 2 options, either true or false. So you can see in the previous one, we had 2 letters, so we had 4 rows. If we had a third letter, we would have 8 rows, because it's the idea that there's 2 choices for P, 2 choices for Q, 2 choices for, let's say, R, 2 times 2 times 2, kind of our dash technique from when we were talking about probability. That gives us 8. And there's going to be 8 rows. Really, who cares? Alternate method for constructing truth tables. There is a shortcut where you don't write out every step, but I would not recommend doing that until you're really good at this stuff. So work from the inside out, write out all the steps. It really doesn't take that long, and it's the best way to make sure you always get it correct. Okay, two statements are considered equivalent if their truth table values are the same for every possible situation. So what I mean is they wouldn't be equivalent if another statement had 3 falses and 1 true. They're only equivalent if it had 3 falses and 1 true in this exact same order, right? So if you set it up the same way with your T's and F's in the exact same order, basically if you just kept this first column exactly the same with your trues and falses, and then you ran a whole new statement, compound statement, whatever it happens to be. And at the end, if you got this exact same false, true, false, false, then that means those two statements are mathematically equivalent. Okay, so that's what it means to be equivalent, is the final result of your truth table has to be exactly the same. Same amount of falses and trues, but also in the same exact positions. Here's an example. If you work these out, I'm not going to spend the time to work them out. Go ahead and do it yourself. Take not P and not Q and work those out, and then P or Q, and then take the negations of all those. You'll see that you get the exact same F's and T's in the exact same places. So that means these two statements are equivalent. So mathematically, if you take the negation of P or Q, it becomes the negation of P and the negation of Q. You basically take the negative of everything, right? You take the opposite of P, you take the opposite of Q, and you take the opposite of the sign. The opposite of the or becomes the and. That's how I always remembered it. De Morgan's laws. And it's basically just the negations of these things that we just saw. So we just saw the negation of the or, right, this one, became the and. Well, it also works the other way. If you negate all these things, you get, right, the negation of P, the negation of Q, and then the negation of the and becomes the or. So these are De Morgan's laws just because De Morgan figured it out a long time ago. Lastly, we can use De Morgan's laws to negate statements in English. So for instance, I made an A or I made a B. Those are both statements, right, separated by an or. Can you see that I made an A is one statement. I made a B is another statement. We can think of this as P, this is Q, and or, remember, is this way. So this really equals P or Q. Now down here we have she won't try and he will succeed. And can you see how if we call this P and this Q, we have an and, which remember is that, and now we have P and Q. Well, according to De Morgan's laws, if we want to take the negation, we get the negation of everything. So not P and not Q. And then this one becomes not P or not Q. Okay, so what's the negation of I made an A? It's I didn't make an A. And then, of course, the negation of I made a B is I didn't make a B. And the or changes to an and. It's just that simple. Same thing with this one, right? She won't try becomes she will try, and he will succeed becomes he won't succeed. You see how we're always negating the verbiage, right? Made an A to didn't make, won't try to will try. So you're always negating the verb and not the adjective. And then, of course, in this last one, the and became an or. All right, so that's all we need to know on how to use truth tables to help us figure out equivalent statements and negating things.